A ball is dropped from the roof of a building. The distance of the ball fallen varies directly. Ooh, direct variation. Y equals kx. Notice what I did. I saw that. I said, I know immediately. That means y equals kx. So I immediately put it down. With the square of the time since it was dropped. Interesting. Different format than we usually talk about, but we'll talk about it later, or that we have talked about. At the instant the ball is dropped, it's traveled 0 meters. 1 second later, it's traveled 4 meters. Find the model that represents the situation. After 3 seconds, how far was the ball dropped? A lot of information. So let's deal with it one sentence at a time. A ball is dropped from the roof of a building. Maybe draw a picture or something. Okay. The distance the ball travels has fallen varies directly with that. Y varies directly with X. Y varies directly with X. Let's make Y the distance, D, and the time, BT. So the distance varies directly with the time. But it's not just the time. It's not that it varies only with the time. It varies directly with the square of the time. So this is where it can start to get a little bit more complicated, and this is where things start to get different from before. If it varies directly with the square of the time, that means that time was squared. So it varies directly with the square of the time means that you just have to square that value. If it said it varies directly with the square root of the time, then you would just square root that guy. If it said it varies directly with the cube of that time, then you would just cube it. So just pay attention to that it varies directly with this. Okay, that's my X value. But if it says the square, the cube root, whatever, that's what you have to do to your input in order to make it work. All right, I've dealt with sentence 1. I've turned this sentence 2, technically. I've turned this sentence into a generic formula. Lots of variables, and so I'm hoping that I'm going to get some values that can help me hone in on this. It says, at the instance the ball was dropped, T equals 0. It's traveled 0 meters. Distance is 0. That's just a point. 0, 0. Cool. That sentence is done. 1 second later, it's traveled 4 meters. Okay, when t equals 1, the distance is 4 meters. That's another point. Awesome. It says, find the model that represents the situation. And then it says, okay, so that's something I have to do. Model equals question mark. Okay, dealt with that sentence saying, okay, I need to solve for this model. After 3 seconds, how far has the ball dropped? Okay, so I also need to solve for distance, dealt with the last sentence. The prepare step of solving for a problem is a very crucial and important part of your problem solving process. So make sure that you take each sentence and turn it into something mathematical. And clues of like, okay, I need to solve for this and I need to solve for this, because then this is when you can start coming up with a strategy, right? You've written it all out. Now look at the connections, see what you can do. Well, I know I need to solve for k. So if I plug in a value like 0, 0, I get 0, 0 equals k times 0. Well, that's not super helpful because I just get 0 equals 0. So sad face, that doesn't help. Thankfully, though, I've been given a second value. I get that 4 as my distance is equal to k times 1, which means that 4 equals k. Awesome. Okay, so now I have all of the information I need in order to write the equation of that model. I just take that and replace k with 4. But I still want distance. I could do distance as a function of time is equal to k, which is 4, times t squared. You still need to have an input and an output, so make sure that you always go back to putting back in your variables. Only solve for the thing that we know needs to be a number, and k needs to be a number. Just like with our quadratics, a, b, and c needed to be numbers. With our cubics, A, B, C, and D need to be numbers. In this case, K needs to be a number, but once we're done solving for that, we need to rewrite it as an equation with an input, T, and an output, D of T. All right, next thing that we need to do, solve for that one, check. Next, I need to solve for this guy. So when time is 3, oh, well, I just need to find D of 3, which means I plug in 3 for T. 3 squared, let's do this on your own. I think you can solve for that guy on your own. Remember that 3 squared is 9, 9 times 4 is 36, and the answer is 36 meters. After 3 seconds, the ball has dropped 36 meters. There we go. This was a huge chunk, not very IB-like in the fact that it wasn't broken up for you step by step. So when you feel like it's just one big problem and you don't know how to separate out all of the information, make sure you take it one sentence at a time and convert it into a kind of like mathy system that you have to represent things. That way you don't have to go back and reread the problem a bunch of times. That way you don't have to go back and say like, wait, what does that sentence say again? What am I supposed to do? Wait, did I solve for everything I was supposed to solve? I put question marks in the places that I needed to solve for. So I had a sort of to-do list of things up here, as well as a strategy of how to move forward. Example 3. The volume of the sphere varies directly. Varies directly means I'm doing y equals kx. Important. Make sure you write that down. With the cube of the radius of the sphere. I'm going to take our previous strategy and do it right now. I'm going to take it sentence by sentence. The volume, y varies directly with x. So the volume, y, varies directly with the cube of the radius of the sphere, x. Okay, we'll have y, the volume be v, and the radius be our input of x. So I'm going to go back and say, okay, volume as a function of radius, output, input, volume as a function of radius equals k times r. But not just r, the cube of r. So I need to take r and I need to cube it. E basta. Well, for now. So now I've taken that first sentence and converted it into what I can, which is, okay, I know I'm using a variation of direct variation, and I'm going to use these variables to represent y and x. You are given that a sphere with a radius of 14 has a volume of that. Okay, so a radius of 14 gives me a centimeters, gives me a volume of 11500 centimeters cubed, which is just a point, right? And if we want to find a direct variation model, we want it to look exactly like this, but instead of a k, we want a number there. And we know that in order to solve for a number, we need to plug in a point. These are the values that we plug in order to solve for k. Go ahead and do that on your own. Plugging in this for our volume, V of r is our volume, 11500 equals k times our radius cubed. 14 cubed is something super large, 2,744. We divide both sides by that, and it gets us probably to a decimal, but I'm going to encourage you to leave these guys in fraction form as much as possible. First of all, because it could be our our slope, if it's a linear equation, which we now notice that direct variation is not always a linear equation if it varies directly with the cube or the square. But also because we're going to be using this formula later on in the problem. And so if you leave it as a decimal, you're going to approximate it and it's going to skew your answers later on. It's like a scan of a scan of a scan. If we use an approximation or something rounded, it's going to slightly change all of our calculations as we move forward. So it's just always best to write things down exactly, especially if we're going to be using that model for later. I just realized that I made the wrong formula. I solved for k, but then in order to turn it into the formula, V of r equals, there we go. And that is actually correct. Okay, and as always, we're going to make a model and then we're going to use the model. So if you were in a test and you couldn't figure out how to do this and you're spending too much time, you make something up and then get your follow-through points later on, because you should show what you do know as opposed to focusing on things that you don't know. So you know how to use a model. Show that you know how to use a model. Move on. Use your model to find the volume of a sphere with a radius of 7 to 3 significant figures. If our radius is 7, that means we're finding the volume when the radius is 7. Go ahead and tell me what that is. 3 significant figures. This is approximately 1,437.5, which means to 3 significant figures, that's our third significant figure. 7 tells us to round up, so it's 1,440 centimeters cubed. Using 6 significant figures, find the percentage error between your model and the volume given by the formula. 4/3 pi r cubed. Sorry, give me just 2 seconds. For a sphere with a radius of 7 centimeters to 3 significant figures. So we are given that this is the actual formula for volume, right? This is the formula for volume that we all know. However, we just created a formula that represented volume, right? Volume is equal to pi r cubed, but we just did something else besides 4/3 pi r cubed. We did something else besides 4/3 pi. We did this fraction approximation of pi and 4/3, which are both pretty tricky decimals, right? So we've got this guy right here, and we used this to approximate what would be the volume using this relationship that we know. So this value right here, correct to 3 significant figures, is our approximation, 1,440. Whereas our exact would come from the actual formula that involved pi. And we're going to use it to 6 significant figures to find our exact. For 6 significant figures, my calculator is here. 4 divided by 3 times pi times 7 cubed. It would round to that as 6 significant figures. This wording is tricky. So the reason why you're seeing me make a face is because I'm looking at what I did for my answer key, and I'm not sure. What I did is I gave the answer to this to 6 significant figures. But here, I'm not sure if it means we should be using 6 significant figures in our calculation. So I'm going to reread it and just kind of double check that I'm doing the right thing, which is a very normal process of problem solving. So it says, using 6 significant figures, find the percentage error between your model and the volume given. So I think so in my answer key, you'll see posted, I used the exact value that I got from here. I left it exact using pi. And I think that I was wrong in that because it says I need to use 6 significant figures in finding the percentage error. So we're doing this, which you have been with me on that all along. I have just not necessarily been with me on that all along. So now I'm going to find the percentage error. Thank you for sticking with me. I think it's important for you to see that I also get confused and wrapped up in circles with the wording of these problems sometimes. Percentage error, if we remember, it's a formula that's in our formula packet. The approximate minus the exact